In chapter 3, the author titled Purple Haze, and it started with talking about two very important discoveries that revolutionized the world of science. Psychotropics or psychopharmacology, the development of psychopharmacology, and the development of antibiotics, and also the change in our perception of mental sickness, and how antidepressant, antipsychotics, and anti-anxiolytics such as chlorpromazine in the 1950s and haloperidol in the 1960s, how these helped reduce drastically the number of the mentally sick within less than 20 years to 50%, and then by 90% within 4 years. The story of chlorpromazine starts with the beginning of pharmaceutical industry, as scientists were fussing around with a substance that has we wouldn't suspect has anything to do with psychiatry, coal tar. Coal tar used to be exploited in many ways to industrialize and soap, shampoos, raincoats, and tropical skin treatment. In the 19th century, they were able to isolate three active chemicals from coal tar. These were naphthalene, aniline, and benzene, and these were to create the building block for the nascent organic chemistry and pharmaceutical industries. Justus von Liebig, a name that's important because as he toured England in the 19th century between the 1830s and 1840s, and he changed the British perception of chemistry, as it was still theoretical in the corridors of Oxford and Cambridge universities, versus Germany, where it was theoretical, practical, and where labs and experiments were used. It was how the Royal College of Chemistry was founded, and August Wilhelm von Hofmann, one of Liebig's students, was appointed by Queen Victoria and Prince Albert as the director or the head of this kind of institute. Wilhelm apprised the monarch of all the newest updates in the field of chemistry and research. Wilhelm von Hofmann had the greatest influence on his students, such as Perkins, who was 18 years old back then, and a young man that was born in 1938. He set up a small lab at his home based on his teacher's advice, and he also enrolled at the Royal College of Chemistry. He was interested in organic chemistry, the chemical synthesis of natural products, and that was the interest back then of most chemistry, because it was no longer just academic but practical. Quinine and the dye indigo were of great interest to chemical research. American natives used the bark of a tree they called Cinchona quinaquina to cure malaria. For centuries, they used this bark to cure malaria. Jesus Spaniards brought the bark of this tree to Europe. The active components was isolated by two French doctors, Pierre Joseph Ripolletti and Joseph Bien-Aimé Gavanto. The active ingredient was quinine. 19th century has known the greatest expansion for the British Empire, including places where malaria was pandemic. So the synthetic of quinine was imperative. It was still being, the back of the tree was still being used, but it was costly, and it was also because the synthesized quinine did not come to the world until 1944. August Wilhelm von Hofmann dedicated the mission of synthesizing quinine to his student Perkins in 1850. He suggested coal tar as a start. Perkin oxidized aniline with potassium dichromate and obtained a black sludge. He used alcohol to extract his product, then he got lilac purple. A dye, this dye was the final outcome. All dyes back then were natural and came from plants and were expensive to get. The color he got was the rarest and most expensive. He decided to commercialize it. He left the Royal College, and this rift led to the creation of chlorpromazine. We're going to know how. He built a small factory at Greenford near Harrow in London for purple dye in large quantities, mauvine or mauve, after the French flower with the same name and color. That's how it was labeled. Perkins' reaction yielded a mixture of isomers of mauvine molecule, a tricyclic ring, 3 ring structures fused together, the chemical structure. Highly important in the field of pharmacology. We are going also to know why. Because it's the basis for numbers of medicines, mainly psychotropic and many others. Mauve made it in fashion and became the color worn by dignitaries. It was said that Queen Victoria wore a dress that was mauve. Most wanted, so Perkin was there to cater. The rise of chemical industry, new dyes were to be synthesized in UK and France. When all this got to Germany, and Germany was there first, it received a serious attention. It was a time where Germany had great chemists such as Adolf von Bayer, Bunsen, Kikuly, and ambitious young chemists were being made in universities. Many students visited UK to learn about the great dye, making chemistry, and went back to Germany. Even August Hofmann returned to Germany. Coal tar dye stuff proliferated in Germany and were all on the Rhine River because for the easiness to use and also for transportation. In 1860, BASF, Bodysch, Aniline, and Soda fabric was established in Ludwigshafen. Hushed Bayer, Kelly, Casella came to existence, and so did industrial research companies. Companies competed to get professional chemists. AGFA got August Hofmann and established a collaboration between him and his students. Perkin decided to make a synthetic alizarin, a plant-derived red dye. They used to get it from the root of madar plant. Grieb and Lieberman, Bayer students at BASF, were researching it also. They came up with the same formula. They synthesized it. They both came up with the same structure, similar structure, and presented their patent within 24 hours. So they had to sit together and share the credit for that dye. A synthetic indigo was to be chased, and indigo has been used for thousands of years, such as by Egyptians to dye the cover for the mummies. It is still used in dyeing blue jeans today. Naturally obtained from Indigofera tinctora. Adolf von Bayer was the one who came up with the synthetic indigo. He was granted the Nobel Prize for his synthesis of the dye-stuff product in 1905. He synthesized the indigo in 1880. Human came with a more efficient and cost-wise synthetic indigo in 1890 and made more profit to the dye-stuff industries, especially BASF. 19th century established the bloom in chemical industry that soon veered its focus to pharmaceuticals. In 1880, many companies in the field of pharmacology found out that aniline derivatives were antipyretics. Now you see, it started as dyes, and then from these dyes that they got from organic matter, they such as coal tar, that they found that had three very important ingredients that would help them later, such as aniline and benzene. So aniline, they found out its derivative, its analogs for aniline were antipyretics. Ludwig Nord synthesized antipyrine in 1884. Then phenacetin came, and it was more favored because it had less side effect than antipyrine, and this was all as they were trying to synthesize quinine. It is the era of nascent pharmacological industry. Dyes are now tested for any potential therapeutic outcome. In 1930s, lead azo dye called sulfamidoxyridine, or Prontosil red, commercial name, was found out to be the prodrug or precursor for something else. It was metabolized to something else, sulfonamide, and antimicrobials. And this is how antimicrobials were ushered in. From fussing around with these dyes, trying to find out synthetic dyes, they came up with these medications. Phenothiazine were born from methylene blue and related dyes. Phenothiazine was another tricyclic at the center of many dyes, including mauve. The magic bullet. 19th century had known the initiation of staining biological tissue with dyes. It was Paul Ehrlich, the father of modern pharmacology's idea, but Graham, the Danish microbiologist, was actually the one who developed a very precise way to stain tissue and microbes to differentiate between gram-negative and gram-positive, the tissue that's going to take the dye and the one that's not going to take it. And this is still being used to differentiate between gram-positive microbes and gram-negative microbes. Ehrlich believed dyes selectively combine with tissue through chemical reactions. They proposed the purpose was to find a dye that selectively combine with microbes and kill them, the basis for chemotherapy. And that's how it's magic bullet. I mean, you stain them, then kill them. He found out methylene blue, when injected in animals, it stained nerve cells. It could be important in psychiatry. The idea was not followed up. Unfortunately, it was not. They did not research it any further. In 1891, Ehrlich found out methylene blue was helpful in patients with malaria. Finally, they thought there is something that can help malaria. It all started trying to find a synthetic quinine. And then they thought, okay, methylene blue could be it. He believed such dye or similar in structure can still be kill both the causative agent organism and the disease. It can call the microbe and the disease. World War II, Germany was short of quinine supplies, and William Perkins and Ludwig Nohr had still not come up with actual synthetic and equivalent of quinine. They decided to put Ehrlich's idea to test and use methylene blue as an anti-malarial. W. Schulman and colleagues at Bayer synthesized analogs of methylene blue and diethylaminoethyl derivatives. It was more efficient but had very serious side effects. In 1931, mipacrin or quinacrine was synthesized. It was widely utilized as an anti-malarial for years to come. Schulman did so by attaching similar side chains to either tricyclic molecules. Chemically, So the author believed that this was a triumph for the German pharmacology and its industry in the late 19th century. The business fell down after it has been organized into big cartels following business styles in USA. Most pharmaceutical industries merged into big pharmas. Example, IG Farben that merged four big pharmaceutical companies. Bosch synthesized ammonia, and he was the guy that led IG Farben together with Duisberg. He was Nobel Prize for it. With Hitler's rise and the alienization of the IG Farben lost its Jewish population workers, and some leaders either died or retired. The aftermath of World War II had known the resurrection of Bayer and BASF. They restarted the German pharmacology, and that's how we're gonna see more products coming up. Chlorpromazine, the first antipsychotic, is an example. Japan conquered most South Asia, cut off the world of quinine supplies, and started a program for anti-malaria research. USA was also cut off quinine. And Gilman and colleagues in USA developed analogs from methylene blue, as if we have talked about, by adding amino alkyl chains to the nitrogen atom of phenothiazine. They came up with ineffective analog as anti-malarial, published their results in 1944. French scientists confirmed the results, and at the Long drug company confirmed their results. Those French scientists had their antihistamine research going on successfully, produced antihistamines such as fenbenzamine and chlorpheniramine. Long researchers have also produced phenothiazine analogs that were unsuccessful as anti-malarial but very efficient as antihistamine drugs. Promethazine, one of these analogs marketed as Phenergan, increased sleep time in conjunction with barbiturate, so it must have an effect on the CNS, right? A French surgeon, Henri Marie Laborit, who was researching drugs to reverse surgical shock in 1949, found out that promethazine, when combined with another pre-surgery cocktail of drugs, patients seemed to be indifferent. Promazine and its derivatives, chlorpromazine or CPZ, had specific effects on CNS. Or to quote the author, had a unique pharmacological profile when tested on animals. CPZ decreased locomotion, increased sleep time induced by barbiturates. Unlike barbiturates, it enhanced learned conditioned behaviors in rats. And as we have seen on the experiments were run on animals. It effectively inhibited apomorphine-induced emesis in dogs. CPZ was given to laboratories and many other doctors. They observed it induced calm, hypnotic state, reduced metabolic rate, and induced hypothermia, analgesia, and as has been quoted by the author, artificial hibernation state when combined with other anesthetics, ideal for pre-surgery shock. It was sold as Largatil, launched, and that's how it launched. The first psychotropic drug was useful as antipsychotic. It was most useful in this field for the treatment of a constellation of symptoms called schizophrenia, a term that was first used in 1904 by Blow. Symptoms of schizophrenia have been categorized into positive and negative. Positive symptoms include hallucinations, delusions. The negative symptoms ones include flat affects, withdrawal, etc. And there's also the cognitive problems that are also manifested in schizophrenic patients, and these are third type of symptoms. Prior to the initiation of actual psychotropic drugs, there were no actual therapies. In 1950s and before that, the treatment for the schizophrenic patient or the manic patient was to induce sleep, insulin shock, lobotomies, and those were really came with really very lethal side effects. Laboratories studied CPZ in conjunction with anesthetics and other meds preoperatively, and found out it induced profound calming effect. It was to be tested on psychiatric patients and administered alone. Now we have seen it administered together with a cocktail of anesthetic and to reduce pain, but now they want to test it on its own on patients. Psychiatrists such as Jean Dillay and Pierre Deniker observed its effect on mentally sick patients. It slowed down motor activity, emotional indifference, and described it as chemical lobotomy. All they observed was this kind of non-emotional patient, stunned, lethargic, and barely moving. And these were called what the syndrome they labeled as neuroleptic syndrome. And this one given at a higher dose to frequently agitated patients. At least people started seeing it's not a magical affliction, but a disorder that needs to be treated. Now, antipsychotics shifted our paradigm of thought. CPZ, chlorpromazine effects spread throughout Europe, Canada, and USA trials were run and results were shared. The field of psychopharmacology was officially ushered in. Ron Poulenc introduced CPZ to Canada, and it was tested and appreciated. USA had initially known CPZ under the name of Thorazine, and by the way, it's still used under the same name. And it was introduced to the States by SmithKline and French laboratories in 1954. It was sold and used as antiemetic. Initially in the United States, it was used as antiemetics. Remember, that's how it started, by reversing the emesis in dogs. So families of schizophrenic patients lobbied for its use in psychiatry when they got news of its lauded effects. Instead of giving the patients lobotomies and insulin shocks and killing them, they said, let's try this. They wanted it. USA Psychiatry was not initially very enthusiastic about CPZ. The trend was that was prevalent was more of a Freudian style one, and psychocounseling. That's of course it works only on patients with less severe mental disorders. Newer generation in psychiatry was more enthusiastic about psychotropics. Evidence-based research proved CPZ to be an antipsychotic medication. Numerous analogs of CPZ were synthesized. Phenothiazine derivatives had a chemical structure that produces neuroleptic activity. In addition to thorazine CPZ, there came others, malaryl, thioridazine, stelazine, etc. Other tricyclic system could structurally substitute, example, thiazanthines. Antipsychotic drugs therapy was established. These particular ones have proven to depress the CNS activity and also selectively affect the positive symptoms in schizophrenics, and they were powerful antiemetics. Side effects were soon to be discovered, and they were kind of very discouraging. EPS, or extrapyramidal syndrome, and tardive dyskinesia. This dyskinesia, actually, those were observed at the beginning, and those are like more like Parkinson-like symptoms. In 1950s, marked the launching of psychopharmacology in addition to antipsychotics, that initially called major tranquilizers. They were called major tranquilizers, antidepressants, and anxiolytics that were labeled as minor tranquilizers. Those also were born. Antipsychotics, new structures, and new mechanisms. Phenothiazine, thiazanthine, and chemically structurally related compounds revolutionized the field of pharmacology. Two other major discoveries happened, one in Belgium, 1934, where Dr. Jane Janssen had a small drug company where he distributed products he got from Jidan Richter. And after the World War started, Richter was killed because he was Jewish, and Johnson lost his major supplier, so he had to do something about it. He decided to manufacture his own drugs. His son Paul A. Johnson took over later. Their pharmaceutical company became one of the giants located in Beers, Belgium. It became even ahead of Sir James Black, who developed beta blockers, propranolol, and cimetidine, Nobel and prized for that. IG Farben synthesized analogs for analgesia during World War II. Pethidine or Demerol meperidine was the first synthesized opiate completely synthetic. Then it was not semi-synthetic, part natural, part it was completely made in the lab. Then they produced methadone, sold as Dolphin in honor for Adolf Hitler. Johnson's chemists altered methadone structurally and produced its analog dextromoramide or Palfium. When Johnson's chemists substituted propionine group for the methyl group on the nitrogen atom of pethidine, Demerol, they got a powerful analgesic effect. And the synthetic product was R951. Then they added butyrophenone group in lieu of the other molecules, and they got R1187 was the product with a powerful cataleptic effect. It causes the person to become rigid, and it causes difficulty moving and insensitivity to pain. Paul Johnson immediately compared it to CPZ. Johnson and colleagues applied themselves to producing hundreds of analogs of R1187 to isolate the neuroleptic effects and analgesic effects of the product. That is how another most popular antipsychotic came to life, haloperidol, was the synthesized R1625 they came up with. Contains two halogen atoms, fluorine and chlorine. First tested on rodents and caused them hypomotility, and it proved to be cataleptic. Doses given 50 times less than CPZ. There existed a belief that connected amphetamine abuse to schizophrenia, the symptoms being paranoia, hallucination, delirium, and psychosis. Example, professional cyclists from Belgium were known to develop that because they used amphetamine and it manifested psychotic symptoms. Second test attempts to antagonize amphetamine effect in rodents, rats with antipsychotics. They gave rats amphetamine and attempted to antagonize the effects by giving them antipsychotics. They observed that haloperidol produced increased more efficient, and it was more potent in reversing amphetamine effect. It also increased motor activity and repetitive behaviors. That is how butyrophenone and phenothiazine and the like became the first line of therapeutic intervention in schizophrenia. Reserpine, the natural antipsychotic. Now we have seen how these, they were synthesized in the lab, and how they started from passing around with some substance that has nothing to do with psychopharmacology or any disorders. They were trying to get dyes, and they wanted to say, okay, let's try and see if we can get medication to malaria, and then how they ended up getting antipsychotics. Now, reserpine is the natural antipsychotic. It's a natural product. The alkaloid reserpine derived from Rauwolfia reserpentina plant grows in sub-Himalaya region of India. It's used in India to calm psychotic patients. Indian researchers found out Rauwolfia reserpentina decreased blood pressure, calmed maniacal patients in 1930s. Western countries' labs in 1950s decided to work with it, and they found out it lowered blood pressure and has a sedative effect. In 1952, the primary active agent was isolated and marketed under reserpine as a tranquilizer and antihypertensive medication. Because when they tested it, they have the same outcome. It was a calming, and it lowered the blood pressure in humans and animals. This is the first time we've seen human. Before it was tested on animals than on humans. Now, side effects notorious for Parkinson disease-like symptoms or APS. Similar to others, it produces the same effect. And it's also seen as depression. 3 types of antipsychotics we now discover and put to use: phenothiazines, CPZ, butyrophenone, haloperidol, and the unique natural alkaloid reserpine. Now here comes the dopamine theory of schizophrenia. Once these 3 types of antipsychotic were produced, phenothiazine, butyrophenone, and alkaloid reserpine, scientists thought this would help them understand the pathophysiology of schizophrenia. Now we know we have created this products. We know the active ingredients in them, and they produce some effect. Now, this must help us understand the pathophysiology of schizophrenia. Molecular structure of reserpine and its pathway of action was to be understood. Reserpine depletes biogenic amines from nerve cells where these were stored. The biogenic amines referred to are serotonin or 5-HT and catecholamines such as dopamine, epinephrine, and norepinephrine neurotransmitters. When given reserpine to animals that were also given L-DOPA, a precursor for dopamine, and norepinephrine, reserpine no longer produces the catatonia and hypoactivity. The revelation was the depletion of catecholamines rather than serotonin was what caused reserpine effects. Further studies revealed that dopamine in particular was responsible for reversing the sedative effects of reserpine if L-DOPA is given. In addition to being the precursor for norepinephrine, it is also very important for motor activity and movement. It is also stored at higher concentration in nerves that innervate the basal ganglia, for example. Dopamine and norepinephrine are identical catecholamines, but separate neurotransmitters, each with separate function. This meant dopamine might be the regulatory neurotransmitter for motor activity. Postmortem studies of brain to patients with Parkinson's disease showed dopamine depletion was considerable. That is how L-DOPA was introduced as a therapeutic agent for Parkinson's disorder. This sparked the idea that other antipsychotics act in a similar way, was as reserpine and depletes the brain of its biogenic amines. It was proven wrong. The effects of CPZ and haloperidol cannot be reversed by L-DOPA. It was then hypothesized that dopamine depletion caused by reserpine or dopamine and CPZ receptors blockade results in inhibition of dopamine-mediated neurotransmitter. So haloperidol and CPZ block the receptors of dopamine-mediated neurotransmission, but reserpine depletes dopamine. CPZ and haloperidol were then considered for counteracting the effect of amphetamine, connected to schizophrenia, as the latter was believed to act directly on catecholamine receptors. It was then hypothesized that overstimulation of dopamine receptors could be the underlying etiology for schizophrenia. Neuroleptics work by blocking such receptors in the basal ganglia. That is also how they cause EPS. Because they block the receptor for dopamine, that's how they cause the EPS syndrome or of extrapyramidal syndrome, but they act effectively on positive symptoms of schizophrenia. Is this how actually neuroleptic work? Have we actually figured it out? Have we actually understood schizophrenia? First, there are other dopamine systems, dopamine nerve cell bodies in the substantia nigra in the midbrain innervate the basal ganglia. When their dopaminergic neurotransmission disrupted, neuroleptics are compromised, and that's how PD results. APS, APS, pseudo-Parkinsonism also happened. Dopamine nerves in other parts of the midbrain don't innervate the basal ganglia, do not control motor activity, but have other functions such as controls of cognition and emotions. So overstimulation of such nerves abnormal results in abnormal behavior. That is to say, schizophrenia. This supports the correlation between amphetamine abuse and schizophrenia symptoms. Antipsychotic drug block dopamine receptors. Biochemical assays were introduced to confirm and measure the effects of blocking dopamine receptors by antipsychotics, such as by Solomon Snyder pioneered this method. He used radioactive butyrophenone, example haloperidol or spiroperidol, and how in conjunction with radioactive substance both bound to dopamine receptors in the brain. It was proved there were more than one type of receptors. D1 and D2, dopamine 1 and dopamine 2, were labeled, and there were more. Neuroleptics bind to D2. They raved on how such finding explains the dopamine schizophrenia theory. What was actually true is that it was confirmed that such antipsychotics cause APS by acting on the way they act on the brain. By blocking certain receptors in the midbrain, they cause APS. Typical and atypicals, or typical and atypical antipsychotics. The coal tar tricyclic chemical structure yielded important psychotropics. Scientists continue to play around around the nucleus to produce antidepressants or new antipsychotics. Wonder Drug Company, Switzerland, synthesized many compounds from the tricyclics, the benzodiazepine nucleus with the antidepressant and neuroleptic properties. Clozapine was burdened, more efficient than CPZ, less side effects, or no EPS. 1967, Sandoz took over and won the research in clozapine cautiously because they considered that lack of EPS was negative of its antipsychotic activity. They said, okay, this doesn't have EPS side effects. It must not be an efficient antipsychotic. So they said, we should just leave it aside. Clozapine showed a different therapeutic profile compared to its predecessors. 1975, trials on clozapine in Finland caused his subject to develop a granulocytosis, which is decrease in white cells and production, and it renders the patient more susceptible for infection. This was also in patients taking CPZ and other antipsychotics with a great margin of difference. Sandoz stopped the trials in 1976. The drug remained available in US based on weighing the outcome and benefits. In 1984, Sandoz started trials on clozapine in USA in multi-sites and showed unique profile, no EPS. superiority to CPZ, improved cognitive deficits. So it was an atypical antipsychotic. Sandoz marketed it, clozapine, as clozaril. To control agranulocytosis, blood tests were advised. Other companies heeded Sandoz line for atypical antipsychotics with no EPS, and that is how Seroquel, olanzapine, Gidan, Risperdal came to the world. Atypical, are they better than typicals? They proved good at addressing negative symptoms, helpful in patients with resistant symptoms. Except for clozapine, it was demonstrated they were all better than CPZ. Most of them come with neurological side effects. The problem with this second generation of antipsychotic, they produce a vast array of metabolic adverse effects, such as what they call metabolic syndrome, obesity, glucose intolerance, dyslipidemia, hypertension. Olanzapine and clozapine are notorious for these drug-induced disorders. Now, and to understand the disease itself, do these atypical antipsychotic drugs help us understand the disease and substantiate the dopamine theory? D2 dopamine receptors are not the binding sites for these drugs. Example, haloperidol. Atypical antipsychotics act on a larger spectrum and act mostly on serotonin 2A receptors. Preferred sites of action for LSD, if you remember, might explain lack of EPS. The dopaminergic theory of schizophrenia even evaluates the efficacy of an antipsychotic by its EPS. Their formula for an antipsychotic is a substance with a powerful D2 receptor antagonist action. How then do a typical one prove or disprove the mechanism of action for schizophrenia? Is it dopamine or is it serotonin? Herbert Meltzer, a psychiatrist, thought a balance between both, when antagonist action could be the answer. There had been new lines of drug ever since, no new drug actually. There had been no new lines of drugs ever since. For 30 years or more, they didn't come up with any new drugs that's better than what they called atypical and typical antipsychotics and depressants or antidepressants. Can animals have psychosis? It's a question. How do we measure psychosis in animals? To try antipsychotics on animals, a model of psychosis in animals is needed. To do so, it is imperative to find out the abnormalities that lead to schizophrenia. These are neuronal transmission and pathways, etc. The drug-induced models, for example, amphetamine, give them some amphetamine and then trigger psychosis-like symptoms, or LSD and trigger what you might understand as hallucinations or delirium, delusions. And then amphetamine produced repetitive behaviors and hyperlocomotion, and LSD produced head twitch and could be understood as symptomology. They presumed that they were symptomatic for schizophrenia or schizophrenia-like symptoms. Phencyclidine, PCP, angel dust, known for inducing hallucination and dissociation in humans, when given to rodents, is exhibited a wide range of behavior summed up as hypermotile, or they exhibited increased hypermotility. PCP does not affect serotonin or dopamine, but antagonizes the action of glutamate, excitatory neurotransmitter. The glutamate receptor affected is labeled NMDA, activated by the amino acid N-methyl D-aspartate. The brain has various nerve pathway systems. Disruption of major neurotransmitters such as glutamate is bound to affect other pathways. Schizophrenics, when observed, showed impairment of sensory motor gating, difficulty filtering sensory stimuli and information. The lack of this PPI, pre-pulse inhibition, and a response to alerting stimuli to major stimuli are on the way. PCP-induced psychosis in animals produce similar symptoms. Behavior. Lack of PPI. Unfortunately, this has been proven to be common to all mental health patients and most neurological patients. Is there a gene for schizophrenia? Studies of twins or close relatives' degree of relation matters have shown some correlation in this trend. But not all twins or close relatives end up developing the disorders when it is in the family. It's more of a nature versus nurture correlation, yet not that much of an exact science. Prenatal care and infancy care, or lack of it, may also be decisive. Is there a gene that might predispose a person to developing a disorder such as schizophrenia? A Scottish family that had a large number of people with tendency to develop the disease had been tested. A gene identified as a scaffold protein, DISC1, DISC1, its role is to bring about other molecules specific types on the cell, specific types of cell signaling. This gene is disrupted. They said they found that this gene, DISC1, that's whose responsibility is to cell signaling or specific cell signaling, was disrupted. So they thought imaging technique have shown a reduction in the thickness of the cortex and also increase in the volume of the ventricles of the brain, variation of the amount of morphology of nervous cells. When they exposed the schizophrenic patient's brain to imaging, they found out these things. The size of population surveyed was not mentioned. The results, we were not told whether they were reproducible, whether they have been reproduced in other, and the research is still going on. So